Now let's talk about intervals of convergence. Basically what we're trying to find is the interval at which a series converges at. And there are going to be two different steps to doing this. The first step is to perform a ratio test. If you forgot what that is, basically it's saying that for a series of a sub n from n equals 1 to infinity, we would take the limit as n goes to infinity of the absolute value of the a sub n plus 1 over a sub n. And we want that to be less than 1 for our series to converge. Second step is to check the endpoints. We plug both endpoints back into our series and check if they converge or diverge. If an endpoint converges, then it will be included in our interval. If an endpoint diverges, then it will not be included in our interval. Now let's go over a practice problem. So we have this series, x minus 4 to the n over 2 to the n. And we want to check if that, and we want to find the interval at which this series converges. First step we do is the ratio test. So, take the limit as n approaches infinity of the absolute value. Okay, so a sub n plus 1, well that's going to be x minus 4 to the n plus 1 over 2 to the n plus 1. And we want to divide this by a sub n. Well, that's the same as multiplying by 1 over a sub n. So that's just going to be 2 to the n over x minus 4 to the n. And remember that we want this to be less than 1. Well, we can simplify this. Let's look at this first term, x minus 4 to the n plus 1. This cancels out with this n, and we're left with an x minus 4 on the top. And we have this n, cancel out with this n, so we're left with a 2 on the bottom. So let's rewrite that. It's the limit as n approaches infinity of x minus 4 over 2. And we want this to be less than 1. Let's get rid of this absolute value and write this as x minus 4 over 2 is greater than negative 1 and less than positive 1. Now all we got to do is solve for x. So first multiply by 2. Negative 2 is less than x minus 4, which is less than 2. And add this 4. So x is between 2 and 6. So that's our first step. Now our second step, remember, is to check the endpoints. So let's start with this 2. Well, if we plug in 2 to our original series, look at the series up here, well, we get negative 2 to the n over 2 to the n. And we can rewrite this as the series, sorry, I should write from n equals 1 to infinity. This is the series from n equals 1 to infinity of, well, negative 2 over 2 is just negative 1 to the n. And that's just going to alternate from negative 1 to 1, and we're adding those terms, and we know that that diverges. So since this diverges, we know that 2 will not be included in our interval. So we still have x is greater than 2. It's not x is greater or equal than 2, it's x is greater than 2. Now let's plug in 6, our second endpoint, back into our original series. So we will get sum n equals 1 to infinity of, well, on top it's going to be positive 2 to the n over 2 to the n, which is equal to the sum from n equals 1 to infinity of 1 to the n, and that's just going to be adding 1 plus 1 plus 1 plus 1, so this diverges as well. So 6 will also not be included in our interval of convergence. So let's just write our final answer. Our interval is that x needs to be greater than 2 and less than 6. Now let's go over on another practice problem where we can see that the endpoints converge. So we have this series, x to the n over root n, from n equals 1 to infinity. So first step is to take the ratio test. So what we have here is the limit as n approaches infinity of, a sub n plus 1 is just going to be x to the n plus 1 over root n plus 1, and multiply that by 1 over a sub n, so root n over x to the n. And we want this absolute value to be less than 1. Well, again, we have this, some simplification that goes on. We're left with an x on top, and, well, that's it. We're just going to rewrite this as the limit as n approaches infinity. The absolute value of, we're left with the x on top times root n over root n plus 1. We want this to be less than 1. Well, if you notice, plug in n is infinity, root n over root n plus 1, that's just going to be 1 when n is infinity. So what we're left with is the absolute value of x is less than 1. So there isn't much algebra left here. We know that x needs to be less than 1 and greater than negative 1. So that's our first step. And our second step is to plug in the endpoints. So let's go ahead and do that. I'm going to plug negative 1 back into x to the n over root n, and we are left with sum n equals 1 to infinity of negative 1 to the n over root n. If you notice, this is an alternating series, and if we want to check if this diverges or converges, well, we need to check one, is this strictly alternating? Well, yeah, you have this negative 1 to the n. Now we want to see, is the limit from n to, as n goes to infinity, of, forget the negative 1 to the n, of 1 over root n. We want that to equal 0. Well, if you plug in n equals infinity, we get 1 over basically infinity, which is 0. So that works. And we want 1 over root n. We want to know if that is decreasing. And it is. You could take the derivative and see that it's negative. You could graph it and see that it is decreasing, but it decreases. So if we plug in n equals negative 1, it converges, and it therefore will be part of our interval. So we can go ahead and put x is greater than or equal to negative 1. Now let's plug in x equals 1. And we get the sum from n equals 1 to infinity of, well, 1 to the n is just, it's always going to be 1 over root n, which we can write as sum from n equals 1 to infinity of 1 over n to the 1/2. And this is just a p-series where p is less than 1, and we know that from 1 to infinity this will diverge. So 1 is not going to be part of our interval. So let's just rewrite our answer. Well, we know that negative 1 works, so x is greater than or equal to negative 1, and positive 1 does not work, it diverges, so x is less than 1. And that's going to be our final answer.